Hi everyone, thanks for tuning in. Today we're going to be talking about optimizing image classification models on the cheap. Let's get started. So we all want to build the best possible models. And ideally what that means is our models would be trained until the end of time on all the relevant data sets in the world. But there are always constraints to consider, including compute costs, wall clock time, deadlines to production, and most importantly, our general sanity. So given these constraints, how can we build the best possible models that have long training times? So to address this, we're going to be using three techniques: transfer learning, multitask optimization, and black box image augmentation. So for transfer learning, we're going to reduce training time. With multitask optimization, we're going to reduce tuning time. And with black box image augmentation, we're going to increase the model performance. Before we jump into our case study, let's just quickly go over some concepts. For transfer learning, we're going to be using fine-tuning and feature extraction as our main methods, leveraging a pre-trained ImageNet model as a hot start. For image augmentation, we're going to do some classic techniques such as horizontal flip, padding, and cropping to introduce healthy noise and increase the size of our data set. But most importantly, we're going to be playing with color jitter, specifically saturation, hue, contrast, and brightness, to see how changing these can positively affect our model's performance. And lastly, we're going to use multitask optimization to effectively tune our model. So here we have a standard SIGOPT hyperparameter optimization loop. So SIGOPT, which is this sigma on the right, is our Bayesian Optimization hyperparameter tuning platform. So SIGOPT will provide stochastic gradient parameters to our model. We'll train our model using these parameters and pass back the model's validation accuracy to then get the next set of parameters for stochastic gradient descent. So it's essentially this loop where over time, using these model validation accuracies, SIGOPT can give us better parameter suggestions, and we should see our model's performance increasing over time. And we're going to run this in parallel because tuning takes a while. So now that we understand how hyperparameter optimization is going to look like, we want to understand what multitask optimization is. And to understand multitask optimization, you really want to start with the simple idea that we can use information from partially trained models to inform our tuning of fully trained models. So more specifically, what that means is that our partially trained models will provide us information about our hyperparameter space that we can leverage to more effectively sample for our fully trained models. So in this example, our partially trained model, which is an SVM classifying MNIST with 1 out of 1/28 of the data set, defines and identifies the blue part of the hyperparameter space as being roughly optimal for our model. And we're able to leverage this to use that information to then sample more in that blue area to inform our fully trained model. So we see this efficiency being useful, and we'll leverage this in our case study. So in our case study, we're going to look at efficiently building high-performing image classification models. For our data, we'll be using the Stanford Cars dataset. It's approximately 16,000 images over 196 classes. And the labels are very granular. They're car, make, and year. And what makes this dataset a very good benchmark dataset is the granularity of the labels itself. The image not only has to identify difficult objects, it has to be able to differentiate very minute differences within these objects, as well as the low number of data points per class also make it a very challenging data set. We'll be using ResNet as our architecture, and we'll be using multitask optimization to tune our models. And as we saw with multitask optimization, a partiality has to be defined. So in this example, we saw Klein using a subset of the data. And what we're going to do is we're going to define our partiality as a subset of the percentage of epochs. So our low-cost task will be 10% of our epochs. Our medium-cost tasks will be 50%. And our full-cost tasks will be 100% of the epochs. For our experiment scenarios, what we're really trying to understand is how can we get the best performing model without breaking the bank on time or compute costs. So we're going to look at different transfer learning techniques and ask the question to tune or not to tune. So looking at how transfer learning is going to work for us, we're going to use fine-tuning and feature extraction as our two techniques. For fine-tuning, we're going to use ResNet 18, and for feature extraction, we're going to use ResNet 50. So deeper networks are typically better for feature extraction, which is why we went with ResNet 50 for feature extraction, and we went with a shallower network to stay on a specific GPU for fine-tuning. And in fine-tuning, what we're going to do is we're going to use an ImageNet pre-trained model as our base, and then continue to train that model on our specific data set beyond that point. And then for feature extraction, we're going to use the ImageNet pre-trained model as a way to extract features from our data set, the Stanford Cars data set, and only train the fully connected layer. So these are the hyperparameters we'll be tuning. We'll be tuning anything related to stochastic gradient descent, as you might do normally. And here's what the optimization loop looks like. SIGOPT will provide us stochastic gradient descent parameters, we'll train our model, and then report back our model's validation accuracy. And so on and so forth, and we should see our model performing better with time. So what did the results look like? We found that fine-tuning the smaller network significantly outperforms feature extraction on a bigger network. And this really speaks to what we chose as our pre-trained model to start with and our data set. Specifically that a pre-trained ImageNet is actually quite dissimilar to Stanford Cars, and our model needed to learn more nuanced aspects of the Stanford Cars dataset to perform well, which it can in fine-tuning, whereas with just a feature extraction, it's not able to do that. And when we introduced multitask optimization, we realized that it gave a significant boost for both methods, but it has a much higher boost in accuracy for fine-tuning over feature extraction, and that just goes back to fine-tuning being a better strategy for this data set and model, as well as the optimization has more knobs to play with and more aspects of the net to affect when fine-tuning is happening over just training the fully connected layer. So now that we see our results, we want to look at what multitask offered as efficiencies at the hyperparameter level. So here we see our learning rate hyperparameter space and the progression of how the learning rate is sampled over the experiment. So specifically in the beginning, we see a bunch of small tasks sampling across the whole space to kind of figure out where the model performs better, followed by medium cost tasks being peppered in to validate and vet stronger areas of the hyperparameter space, and at the end we see a handful of full cost tasks really zoning in on a specific area of the hyperparameter space that really works for the model. What did the misclassifications look like? So a lot of our model's errors were close calls, where in the Aston Martin example, it would either get the make or the year of the car wrong. It had problems with unconventional angles, and it had problems with background clutter, where it was unable to identify which object in a noisy image to focus on. Which brings us to our next question is, can we improve these results? So we hypothesized that a lot of the errors we saw with the model was due to the properties of the dataset, specifically not having enough images per label and the granular aspect of each class combined make it very hard for the model to differentiate between car, make, and year. So we thought we'd get around that by generating synthetic images with multitask optimization. So here, what we're doing is we are introducing image augmentation as a pre-processing step prior to our model training. So our model will now be trained on augmented images and original images. We'll vet the model performance with the original images, tell SIGOPT what the performance is for our validation, and SIGOPT now suggests hyperparameters for our image augmentation process as well as our model training process. So our image augmentation process, pretty simple. Each image is going to go through a horizontal flip. It'll be resized and randomly cropped. And where SIGOPT comes in is in suggesting parameters for our color jitter, specifically saturation, hue, brightness, and contrast. So our new experimental design will keep all the properties of our current best performing model, which is the ResNet 18 fine-tuned and optimized. And we're just going to add image augmentation to really see if we can beat our current baseline. So this is what our current baseline looks like. It's the ResNet 18 fine-tuned and optimized with multitask, and it's at 87% accuracy. And we're going to see by adding image augmentation, can we beat this baseline? So this is what the new tuning loop looks like. So SIGOPT will provide parameters for color jitter, where we will run the image augmentation process. Our model will be trained using the augmented data, the original data, and the stochastic gradient descent parameter suggestions from SIGOPT. We will run our validation on the original dataset and return that accuracy score back to SIGOPT. And SIGOPT will then provide a next set of parameters for image augmentation as well as our training process. And really what we see happening here is that we're able to leverage a technique such as Bayesian optimization to inform a classically uninformed / unsupervised process that is image augmentation. And we're able to leverage the model's downstream performance to help us navigate the image augmentation parameter space to understand which parameter values really work for our model, which I think is pretty cool. So these are the hyperparameters that we will be tuning. We have a set of stochastic gradient descent parameters as well as augmentation color jitter parameters. And the results are pretty cool. So we get a 10% boost, including image augmentation and optimization from just a standard ResNet 18 without optimization. And we get a 6% boost from our current baseline, which is the ResNet 18 and multitask optimization. So this is a pretty high increase in accuracy, which really asks the question, what do the augmented images look like? So on the left column here, we have the original images, and on the right column, we have the augmented images. So what we see is that the augmented images are hyper-vibrant versions of our original image, where saturation, hue, and contrast are extremely heightened to really draw the differences between the car, the ground, and the background, and make those distinctions very clear. We also see that, as in row 2, that images in the background of this banner, for example, are able to be pulled into the foreground and made more obvious through this augmentation technique. We don't really know why the model would needs images to look like this. Obviously, it would be really interesting to do more work in terms of interpretability and understand if these attributes are transferable between models and different data sets, but that's not something we've done so far. This just kind of happened, and it's really cool to see what the augmented images look like that actually worked for the model. So given these, what did misclassifications look like? So we still had some close calls in terms of make and year, as we did previously, and we still have problems with difficult angles. But we seem to be able to solve the problem of reducing problems with background clutter. And we think it's because of these hyper accentuated boundaries between objects in an image that make the model be able to really understand which aspect of the image to focus in on and which aspect matters and which does not, which is really cool. And to solve these problems of close calls and difficult angles, we hypothesized that by just increasing the number of images per class even more would help with that, as well as including rotations in our augmentation process. So why does this matter? With our transfer learning results, we see that efficient optimization paired with efficient training techniques allows any team to build high-performing models. And with our augmentation results, we see that by including optimization earlier in the modeling process, we are able to get better model performance and learn more about our data. And we're able to leverage techniques such as Bayesian optimization to really inform classically trial and error processes and be able to leverage information we know about our model to really guide these unsupervised techniques. So again, I work at SIGOPT. If you have any questions on any part of this presentation or would like to play around with our product, please feel free to email me or go online to sigopt.com. So thank you, everybody, and stay safe out there.